Yeah, so good evening, everyone. Uh, Welcome to the DSA Carnival 2K21. Today is the 10th day of the carnival, and I'm Anurag Mishra from IST Indore, and I'll be the host for today's session. I hope you all are enjoying the session. So let's move towards the today's session. The topic for the is trees, and the instructor for the today's session is Mr. Waqar Ahmad, which is well-known personality. Okay, so he's the owner of the CodeNcode channel on YouTube and a power programmer at Infosys. Okay, so I think the introduction you already know. And at last, the quiz winner will be announced, and the quiz link will be also circulated. And the winner of the quiz will get a t-shirt from the Prep Byte. So without taking too much time, let's start the session. So over to you, sir.
Oh, thank you, Anurag. Hello, guys. This is CodeNcode, as you guys might already know. So, cutting all of the introduction, that is not much important. Let's straight back to our lecture. So today we'll be covering most of the tree algorithm. Not There are 4 or 5 algorithms that we'll be covering. First, we'll be learning how we represent tree data structure, and what are the different traversal techniques like BFS and DFS. And then we'll be learning about the diameter of the tree, how you can find it. And also, after that, I think we have one more topic to cover. Okay. LCA, yeah, that is most important. Lowest common ancestor. When you are given a tree, you are given 2 points. You have to find their LCA, that is lowest common ancestor. Okay, so let's start. So before starting, Anurag, are you there? I think. Hello.
Yes, sir.
So Anurag, this session will be interactive, right?
Yeah, sure.
So I'll be getting all of my comments. I'll be interacting with the students in the comment section.
Yeah, in the
Okay, okay,
comment
okay.
section.
Thank you. Okay, so guys, if you have any doubt, or if my pace is not correct, you can always post a comment telling me that I should pace up or slow down, depending upon the situation. Okay, in the comment section. So let's get started. Let me just share my screen real quick. Okay, so I think screen is visible. So let's start with the tree representation. So first of all, what is tree? Here on the screen that you can see, this whole thing is actually a tree. So in tree we have two things. First of all, these entities which are known as the nodes, and then the relationship between them that are known as the edges, right? So uh, first thing, we have to learn how to represent this thing in data structure. Okay, so there are two most widely used techniques to represent the structure of the tree. First is adjacency matrix representation, and the other is adjacency list representation. We'll be learning both. So this graph, this tree that you see, this can be anything, like these entities can be destinations, different destinations, and these can be roads connecting them. These can be cities, and these can be airline connections. So we have city A, we have city B, there is one airline facility from A to B, and so on. So these represents real life structure, and you will encounter them very much, even in the social media network. You have, like, this is a person A, and then he's directly connected, or basically friend, with B and C. Okay, and then B have friend like D and E. So you might get notification in Facebook, like the B sorry D and E are friends of your friends, would you like to connect with them also? So this is how it is done. Friendship structure is represented somehow using the graph. Okay, the internal implementation, I'm not so sure how Facebook does it, but most of them, they are using graph data structure to store the relationship of friends, and then using this they can get many information, like how many friends you have. For example, for this person, how many friends it had? Only two. Number of edges which are directly connected to it. So this is about graphs or tree. Tree is a subset of graph in which if there are n nodes, okay, so these entities that you see are actually nodes, and the entities are connected by the edges. Okay, so we'll call edges. Okay, sorry, my writing not so good. So we have edges. Okay, we'll be representing them by E, and then we have nodes, will represent using V, and if I use certain different notation, I'll let you know. So basically the question is how you will represent this whole structure. Okay, so let's name them first. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So we have two different kind of representation. One is adjacency matrix representation. So I need to remove all of this and start with the very basic graph which I can show you using representation of matrix, because that is going to take a lot of space. So suppose you have a simple tree structure like 1, 2, 3, and 4. Okay, so you will have a matrix of size 4 cross 4. How many nodes we have? 4, and that's why the size of the matrix will be 4 cross 4. So this is the matrix. So 1, 2, 3, 4, these are columns. 1, 2, 3, 4, these are rows. So now since this whole row will represent the status of node 1. Okay, so node 1 is connected to node 3 and 2, right? This is 2, my bad, I'm not used to work with this pen tab. So this is node 2. Node 1 is connected to 2 and 3. So in row 1 at column 2 and 3 we will store 1, which represents node 1 is directly connected to node 2, node 1 is directly connected to node 3. The rest of the cells in the row 1 will be 0, because node 1 is not directly connected to node 1 or 4, right? There is no edge directly connected to sorry, this will be 1, because every node is connected to itself. So this whole diagonal will be actually 1. Node 1 is directly connected to itself, it is connected to 2, and it is connected to 3. That is why 1 1, 1 2, and 1 3 are 1, and this is 1 4 is 0, because there is no direct connection from node 1 to node 4. So you might already have guessed what will be row 2. Row 2 will be 2 1 will be 1, 2 2 will be 1, because node 2 is connected to itself. There is no direct connection from node 2 to 3, so 0 and 0. Similarly, let me fill for the other ones. For 3 we are directly connected to 1 and 4, this is 0, and for 4 we are directly connected to 3 only, so 4 4 is 1 and 4 3. So this is how your adjacency matrix representation will look like. Okay, so you will have a matrix, and then if there is a connection between node A and B, you will be provided input with edges. So if you are given with n nodes, you will be provided with n minus 1 edges, because in tree if there are n nodes there will be n minus 1 edges exactly. So they'll be providing you n minus 1 edges. So input will be like 1 2 for this edge, 1 3, and then 3 4. Okay, so each time you receive AB, which represents a single edge, what you can do, you can have an array AR, doesn't matter what you name, and then at position AB you can set it to 1. Same goes for position BA, you can set it to 1. So this is how you process all of the edges. Okay, so this way your adjacency matrix representation will work. And now one important thing about this is drawbacks that you must know about this representation. See here, as you can see, if there are n nodes, it requires let me just use some other space. So okay, so here, what is the space complexity? That means how much space you require. If like there are n nodes in your tree or graph, then space that you require to store them will be n square. Okay, so if input is of size 1 million, then you require 10 power 12 integer size of integer array, which is a lot, and most of them will be wasted because they'll be storing 0, most of them, because not all nodes are connected to every other node in tree. In fact, a graph, it is possible, but in tree not every node is directly connected to every other node. Okay, so we see that the drawback of adjacency metric representation is that it uses a lot of space. The thing the one of the properties which is very good for matrix representation is that you can very quickly find out whether two nodes are directly connected or not. If I ask you whether node 2 and 4 are directly connected or not, you can directly go to cell 2 4. Either you can check 2 4 or you can check 4 2. Both of them are representing 0. That means they are not directly connected. Okay, so in constant time you will be able to find out whether the two nodes are directly connected or not. But when you go for the next representation, that is adjacency list representation, you won't be able to find out in constant time. But the thing about adjacency matrix is adjacency list representation is that it uses linear space, it doesn't use quadratic space. Okay, so let's see what is adjacency list representation, and then we'll take some questions from this, or maybe if I have to show you through implementation, we'll go with that as well. So for the same graph, let's go for adjacency and adjacency list representation. Okay, so see here, for each node what we are going to do, we are going to have a flexible list. Okay, so for node 1 I have a list. What is this? Okay, sorry. For node 1 I will have a list. Okay, for node 2 I'll have a list, and for node 3 I'll have a list, for node 4 I'll have a list. So node 1 is directly connected to node 2 and 3, so list size of node 1 will be of 2, and it will store 2 and 3 because node 1 is directly connected to node 3 and 2. That's why it is having a list of 2, right? Node 2 is directly connected to 1 only, so 1. Node 3 is connected to 2 elements which are 4 and 1, so 1 and 4, and node 4, this is 4. Okay, node 4 is directly connected to only 3, so it will store 3. So here you see space that we are using is very much, I mean very less as compared to adjacency matrix representation, which requires n square space. Here the space is only linear, not quadratic. Okay, so this is one of the major profit that you get using adjacency list representation. And how you can implement it, so you can have a vector in C++. You can have an array of vectors like vector of int, and then have an array of size n. Okay, or n plus 1 if you want to work with one base index system. So each node will get its own vector basically represents your list, so adding and removing from the list at the back only takes constant time. So if you have a vector like this and there comes an edge AB, so what you can do, you can go to AR of A. I'm talking about the vectors. Okay, I'll show you with an implementation if needed. AR of A dot push back, PB is for pushback, B. Okay, so in the adjacency list of A you added B, and same goes for AR of B dot pushback A. So in the adjacency list of B you added A. So this way you are adding elements at the back of the list, because in list of A we need B, in list of B we need A, depending upon whether this is directed or not. For now we are working for undirected. Changing it from directed to undirected is very easy. We'll not cover that. So yeah, this is adjacency list or adjacency matrix representation. This is adjacency list representation that we have learned about, and then we have learned about adjacency matrix representation as well. So let's see if we have any question before we move on to other. And if you want me to show you some practical implementation, we can do that too. Okay, so do we have any questions? In the chat box I can't see anything. Am I audible, by the way? Oh, sorry. This is private chat. Oh, my bad. That was private chat. I have to go to comments. Okay, sorry. So, okay. Most likely. Uh, Surinder asked whether this is a session on graph or tree. No, this is a session on tree. But the thing is, tree is a subset of graph. To explain tree, we have to go through graph. That was I was explaining a little bit about tree. Oh, sorry, about graph. So, okay. Do we have any questions related to the two representation method that we just saw? Or should I show you through implementation? Rohan says the seems like the session is not interactive. Sorry, I didn't know that I had to go to the comments. I thought this is the place where I'll be getting. Oh, sorry, my screen is actually not here. It is now visible. See, I was looking at this screen. I thought I'll be getting all of the comments here in the private chat. Okay, I didn't knew I'll be getting the comments here, so that's why I didn't see the comments earlier and didn't respond. So yes, you are audible, no doubt, sir. Mm-hmm, mm-hmm, mm-hmm. When do we use that? Usually, most likely that the session that we are getting is for those guys who are going to prepare for either technical interview rounds or for the participation in the competitive programming contest, right? So in the competitive programming contest, you will be getting a lot of questions related to tree or graph. When you think about real life examples, you will be learning this in networking, where you learn about the different routing models in the routers. When you are working with networking, you will be learning about that, so that will be implemented using graph algorithms are used there in the networking. In social media sites, of course, your relationship is used or representation or stored in the system using graph, most likely, since we do not know the implementation how they are implementing, but most uh, beneficial way will be to store the all of the relationship using the graph data structure. So yeah, these are the and also you use Google Maps, right? So in the maps also you'll be seeing all of the destination that you have, like I want to go here or there. Those are represented by the nodes, and the roads are represented by the edges, and graph algorithms are used to find the shortest distance between one point to another. So real life, there are many real life implementation of these algorithms that you will be learning. Can you please explain that up to what limit should we use adjacency matrix? So see, Raja says, see, usually you should not create an integer array of size greater than 10 to the power 7. Okay, you should not go beyond 10 to the power 7. If you want to see why, there is also, whenever you are working on any online platform, be it CodeChef, CodeForces, you will be given two things for each question. You will be given time limit, and also you will be given a memory limit. So you see, if you are taking an array of size 10 to the power 7, uh, sorry. So if you are taking an array of size 10 to the power 7 of integer type, it requires 4 byte, right? So these many bytes you are using to convert it into kilobytes, divide by 10 to the power 3. To convert it to megabyte, convert it divide by 10 to the power 3 again. So if you are creating an array of size 10 to the power 7, it is going to take roughly around 40 MB. Okay, if I'm making some calculation mistakes, please let me know. But if you are using an integer array which takes 4 bytes, okay, and you are creating an array of size 10 to the power 7, these many MB of space, you are using 40 MB. If you go for 10 to the power 8, simply multiply it by 10, so 400 MB. If you are creating an array of size 10 to the power 8, it takes 400 MB, and you will be given with the memory limit, and depending upon that, you can decide how much space you are going to use. Most likely, when you are working with 2D array, you should not go beyond 10 to the power 3 into 10 to the power 3. Okay, most likely you should not go beyond 10 to the power 7. Okay, so that you should keep in mind. don't go beyond 10^7. That may cause MLE, that is memory limit exceeded, or also to process this amount of memory, it can also cause time limit exceeded, TLE. So okay. uh, is, is it necessary to learn recursion before trees? The answer is yes, actually, because if you are going to use DFS, which will be used a lot, even for advanced algorithms that you work on trees, you need to have the knowledge of recursion, because you will be applying DFS. Even to apply DP or other algorithms, you need to have the knowledge of DFS, and that's why you need to have the knowledge of recursion. Yes, that is correct. So someone is asking for practical implementation. Let me just let's go for practical implementation as well. I hope we are not wasting too much time. Okay. Just setting up the screen. Ooh. Okay. Now screen should be visible. Okay. Can anyone confirm, is this screen visible? No. Yeah, I thought so, because just a second. Share the screen. Okay, this one share. Okay, yeah, now it should be visible. Okay, so if we are going for practical implementation, see, for adjacency matrix representation, you can create an array of size like, depending upon what is the number of nodes. I'm going for 1000 cross 1000 because I'm assuming the maximum number of nodes can be 1000 at max. So you'll be provided first n, the number of nodes. Let me increase the font size. This should be visible. You'll be provided with n, the number of nodes, and then if number of nodes are n, number of edges are n minus 1 if you are working with tree. Okay, for graph it can change. So each time simply read a and b, and then in the array ab set it to 1, and also ba set it to 1, right? The other places are already set to 0, because when you declare an array globally in C++, at least all of the values are initialized with default value. For integer it is 0. Okay, so all of the cells are already containing 0. You only have to change those which are provided in the edges, right? So AB is an edge, so cell AB and BA both should be 1, and that is exactly what we are doing here. So we have taken input, and now our graph is set. Now you can perform algorithms like you can perform DFS or BFS on this graph. For now, let's just simply print it. This is a for loop that's run from 1 to n. Okay, jn simply. For now, I'm printing only, and I was showing you that this is the only line that you have to write to read and create the array, the graph. Let's see out, and we haven't learned about DFS or BFS. That's why I'm not going for DFS or BFS representation. Just in a moment we'll be learning about that. So if suppose let's input the same graph that we created here. So the graph is, there are 4 nodes. Increase the font size of this as well. This should be visible. There are 4 nodes. One is connected to 3. One is connected to 2. 3. 3 is connected to 4. Okay. So here you see, this is your adjacency matrix representation. Oh yeah, I forgot one thing. Since every node is connected to itself, I have to set this manually, this diagonal. So for diagonal, you can run a loop here itself. Before doing anything, you can run a for loop and set the diagonal I to be 1, because each node is connected to itself, right? And so this is, let's input this graph again, increase the font size. 4 nodes, one is connected to 3, one is connected to 2, 3 is connected to 4. Okay, here you see. see diagonal, left leave here. One is connected to 2 and one is connected to 3, right? Because 1 2 and 1 3 are set to 1. Have you see, right? And same goes for node, let's see for node 3, 3 is connected to 1 and 3 is connected to 4, right? So this is how your adjacency matrix representation works. So this is how you take input in adjacency matrix representation, and this is how you create the graph, right? In adjacency list representation, instead of vector, what we instead of this, what we have 2D array, we have vector of int, array of vector of int. How many nodes can we have? I'm assuming we can have 10 to the power 5 number of nodes. So basically I have 10 to the power 5 different list, right? So okay, now what we are doing, we are reading n-1 edges, and now what you would do in the adjacency list of A, simply insert pushback. Pushback is function used to insert element in vector. Okay, in the adjacency list of A, insert B, and same goes for in the adjacency list of B, insert A. Okay, this is your graph is done. For each node you can print all of their nodes. So int node in the adjacency list of current node, which is ith node, then simply print node space. So now what we are doing, we are reading the graph. After that, what we are doing, we are printing for each node its adjacency list is what we are printing there. So again, there are like 4 nodes. One is connected to 2, one is connected to 3, 3 is connected to 4. So for node 1 is connected to 2 and 3. So that's why we are getting output 2 and 3. Node 2 is connected to node 1 only. Node 3 is connected to node 1 and 4. That's why in the adjacency list of node 3 you have 1 and 4. Node 4 is only connected to 3. Now you might have a question why we are not having in each node, why we are not having itself in the node, right? In the adjacency list of that node. You can tweak it. You can do it yourself. We don't actually need that when we are working with adjacency list representation and we are applying BFS or DFS. Okay. So last question that I took was this. Yeah. So we have covered 2 things, both the representation method of tree. Now we have to learn about the traversal techniques. So there are 2 traversal techniques. Till now everyone is clear. I mean, no doubt till representation, right? Anyone? Okay, I'm not getting any response. So I'm assuming that till now we are all clear. Okay, so let's go for DFS and BFS. For that, let's just increase the size of this node 1 2 3 4. Oh, sorry. Node 5, node 7, and node 6. Okay, so this is the tree we are working with, and let's go ahead and learn about DFS first. DFS, that is depth first search. Okay, so the basic idea of depth first search, there are 2 traversal techniques. Traversal techniques means traversing the whole graph one by one in certain way. So in DFS, traversal technique is that you start from certain node, you can call it root, and then starting from there, you go one by one, choose certain path and go as deep as possible. That is DFS. For example, just randomly choose a path and keep going down, right? When I said go as deep as possible, doesn't mean that you have to take this path. No, a DFS can start from node 1 and can go this path as well. So basically, choose a node and then randomly choose another node which is not visited and directly connected to the current node and move there. From here, again, go to the node which is not visited, again choose certain node which is directly connected to this and is not visited. So basically go here and so on. So this is how DFS works. So let me explain this in details. Before that, let me see if there are any questions. No. Gaurav says hello. Okay, hello Gaurav. So this is tree session, please explain traversal of tree. uh, actually pre-order, post-order, and those are specifically for you can say binary, ternary, or canary tree. We are learning here about the general tree. In fact, the DFS or DFS and BFS lie in one of these categories. But let me see, can I? And we are in this session only going to cover BFS and DFS. Okay, maybe on some other day we will cover pre-order, post-order, and in-order traversal, because we only have limited time and I cannot explain, and I have to cover a lot of things. So that question is not relevant to the lecture. So I'll be answering that in a moment. And by the way, Infosys, I'm working in Infosys. So a DFS. So first let's learn about DFS. The basic idea is start from certain node. For example, we are going to start with the node 1. Okay, we are going to start from node 1, right? From this node, what you will do, you need to keep track of which node you have visited already. Okay, so you can have a visited array of boolean type. How many nodes do we have? 3 4 7. 1 2 3 4 5 6 7. Okay, node 1 2 3 4 5 6 7. You need to keep track of which node you have already visited. Okay, so I'm for that I've created a boolean array, and I'll 0 represents that node has not been visited, and 1, basically true, will represent that node has been visited. For now, none of the nodes have been visited. So how your DFS will work, from the graph you will pick a node and then run a DFS on that node. Okay, for example, I started from node 1. Okay, so now you reach node 1. What you would do, in the visited array, you would mark node 1 as 1. That means it is visited now. From node 1, pick any node which is directly connected to it and is not visited till now. So node 2 is not visited. So from here we will move here, and now we are at node 2. As soon as you reach node 2, you will mark node 2 as visited as well. So now what you will do, in the adjacency list of node 2 we have 5 and 1, right? So we go to 1, but 1 is already visited. We check whether 1 is visited or not. We can see 1 is already visited, so we are not going there. We check for 5. 5 is not visited, so we would move on to 5. So you see, starting from here we are going to as much as possible, right? For now we are at node 5, right? So mark it as visited. Now repeat the same process. Go here, node 7, mark it as visited. Now track back, because node 7 does not have any nodes which is not visited and is directly connected to node 7, right? So the work of node 7 is completed, so it would go back to the node which has made a DFS call to this node. So we'll go back to 5. 5 checks, are there any other nodes left? The answer is no, so it would track back again. So here you can see this is actually recursion, right? So you need to have the knowledge of recursion to understand this completely. So from node 5 we would track back to node 2. Node 2 has nothing to do, so we would track back to node 1. Node 1 sees, are there any other nodes which are not visited and directly connected to me? Answer is yes. 3 is directly connected to node 1 and is not visited, so we would go back to 3. Now we are at 3, mark it visited. For 3 we would repeat the same process. Node 4, 4 is marked visited 1, so nothing to do for node 4. Track back to 3. Yes, there is to visit something in node 3, so we would go to node 6, mark it as 1, and everything's done. So we would track back to node 3, nothing to do here. Track back here, and from here we would return to the place where we made DFS call on node 1, basically in the main function. So this is how your DFS traversal works. So for DFS you have to have this array. To be honest, you don't need, once you are comfortable with DFS, you actually don't even need this array. You can actually keep for each node its parent detail, and then you can go with that without using this array. But at the beginning stage, at the beginner's level, I will highly recommend you to use this visited array. So this is how your DFS work. Okay, so let's run this DFS. Let's implement it on this tree itself. Do we have any question regarding, let's first implement this and then we will take questions. Okay, so this is how we are creating the graph, okay, using adjacency list. So I'm not going to do anything here, and simply what I'm going to do is run DFS on node 1. Okay, and here you see, let's define DFS. So this is the DFS array which will traverse, which will traverse this whole tree one by one, right, in the manner in which DFS is supposed to visit. So now we have a visited array of type bool, right? This is a visited array of type bool. Again, since I'm declaring this globally, so all of the values are initialized with 0, which means not visited. So as soon as you reach certain node, what you do, you mark it as unvisited, right? I mean, sorry, visited, right? So that is exactly what we are doing here. So I'm marking the node 1, current node, that is node as 1. That means it is now visited. After that, for each node v in the adjacency list of current node. So what I'm doing, I am traversing the adjacency list of current node. So basically, when I'm traversing for node 1, what is happening? Node 1 has its own adjacency list, right? We have just learned that. And in that, we have 2 and 3, right? So what I'll do, I'll traverse them one by one and see if it is not visited, make a DFS call there. If it is not visited, make a DFS call there, and so on. So this is how your DFS works. So now you are traversing the adjacency list of current node one by one and checking whether current node is visited or not. So if current node, which is V, is not visited, simply make a DFS call to that node. As simple as that, and your DFS is complete. So how you would know that we are visiting the node in correct order? So let's simply print it. Okay, so what we are doing, we are running DFS and simply printing the nodes in the order they are visited. So let's input this tree and see what is the order in which they get traversed. Okay, so there are like 7 nodes. One is connected to 2, one is connected to 3, 2 is connected to 5, 5 is connected to 7, 3 is connected to 4, and 3 is connected to 6. Here you see, so this is the order in which they get traversed. So see here, first we started from node 1, so of course node 1 will be printed. So I start traversing nodes 1's adjacency list, right? And I see, okay, in the adjacency list of node 1, I have 2. Is it visited? The answer is no. Till now, we have not visited 2. So I'll make a DFS call to node 2, because in the code, if node 2 is not visited, current node V is not visited, make a DFS call to node V, right? I check whether 2 is visited. The 2 is not visited, so make DFS call to 2. So basically, I went from 1 to 2, and then 5, and then 7. So this is the order we followed. So we would track back, track back, track back. From here, we would go to 3, right? Go to 3, and then we went to 4, and then track back, and then we went to node 6. So this is how your DFS traversal works. This will go as deep as possible. This can be used to find the height of a rooted tree, right? How that is that I need to cover in different lecture, because in the given time frame I'll not be able to cover all of the algorithms in a single lecture. Okay, so this is how DFS works. This is the implementation. Do you have any questions? This is Sai again ask. No, this is a session on tree, which is subset of graph, so we can assume that this is a session of tree, I mean graph. Do we have any question on DFS and its implementation? Anything that you missed? I need to. Okay. Uh, just take 2 minutes and print and post any question you have. Okay. I need to put my laptop on charge, because. Okay. Sorry for the inconvenience. Okay. Okay. Now all good. So. Okay, Rohan says too far. Okay, so Rohan, the thing is, in lectures like these, we are given a time frame and we have to complete these many concept in a single lecture. Like I have to cover like 5-6 concept in a single lecture of time frame of 1.5 hour or 1 hour 45 minutes. So that's why I need to keep a pace a little bit higher. This all of these lectures are also available on my channel, and also there are great teachers like Gaurav Sen and Eric To and other channels which have covered this in details. So you can learn from there as well. But here I'm trying to give you a high level idea along with as much clarity as possible in the given time frame, because if I take too much time, I won't be able to cover all of the topics that I've given to cover in this session. So I have like 4 other topics to cover as well, and in fact I'm going too slow with it, if I consider that how much time I've left. So okay, how to search for an element. Basically, this question should be regarding tree, right? So you might your question maybe what I'm able to understand is this. For example, node 3 you wanted to search whether it is directly connected to node 4 or not, right? That is what you meant by your question, that how we can search an element, or nipun. Okay, so in that case you have to traverse the whole adjacency list of node 3. There is no other way around. So it will take big O of E time, where E is the adjacency set, size of the size of the adjacency list of node 3. Okay, there is no other way around. You have to go through all of the nodes one by one. What you can do, you can change. In fact, instead of using vector, you can use set, and then you can take login time and n is the size of the adjacency list of node X in which you are going to search certain element. Oh, Gaurav says is DGDP also in CodeNcode. Yes, I have covered DGDP as well. Give an example of binary search tree. I'm sorry, Rakesh, that will make this session lengthy. Or binary search tree itself is a vast concept to cover. There are a lot of things regarding binary search tree, and not all of that can be covered here. And since you are only asking to give an example, even though I have to explain what is binary search tree and then with an example, so that would take time. So unfortunately, for this session, I can't do that. Suggest good channel for studying trees and graph. I have my channel, and I don't know whether Ericto had covered or not, but maybe Gaurav Sen has covered it. I don't actually know many channels. Believe me, it's not like I'm trying to uh, sell my own channel, but literally I do not spend much time there. There are 3 or 4 channels I know. If you want to learn college level data structure or algorithm, there is someone, even I'm forgetting the name. Sorry. So there is Tushar Roy. I think most likely he might have covered it. I have covered most of the algorithms of graph or tree, and also there is Gaurav Sen, Eric To, and also there is one more channel which is my personal favorite, Algorithms Live. That guy goes into too much details, and I just love about that thing about his channel. So yeah, that's what I'm thinking, Vinay. But the thing is, most of the students might not be able to understand the pseudocode. So yeah, Rohan says that Striver sir have already covered. So most likely Striver, if I'm not wrong, Striver's channel name is Take You Forward, right? So Rohan says that he has covered. So yeah, Striver's has already. He also have covered graph algorithm. So you can watch from there as well. So okay, I'm not seeing so many questions regarding DFS, so we'll move on. I'm assuming that most of you guys have a certain idea that what is DFS. Okay, so now let's go for BFS. BFS you can use to find the shortest thing. Okay, you can use it to find the shortest path. And shortest path, by shortest path, I don't mean to say that in weighted graph. I only mean to say by unweighted graph. What is this? Okay. Let me just delete this. Now let's go for BFS, that is breadth first search. Okay, let's just use this. I hope this is able to cover all of these things. Okay. Great. Oh, okay. This color, this. 1, 2, 3, 4, 5, 6, 7. Okay. Uh, yeah. So this is, so see, this is, I need to change the graph a little bit more so you understand what is BFS. So 5, 6, 7, node 8, I messed up, node 8, 9, this is going to take a lot of space. Okay, so now I need to increase the size of this array. we already have 7 elements, so let's go for 8, 9, 10. Okay, and now this is BFS, not DFS. So now we are going to learn about BFS, that is breadth first search. So using BFS, you can actually find out the shortest path from certain node. Shortest path, by that I mean when we have graph which doesn't have weighted edges. What is weighted edge? So in the tree you can also have each edge can have its cost. For example, if these two are cities and this is the road, it can describe that the length of the road. Okay, so that is called weighted graph. For now I'm not working with weighted graph. So what you can do, for example, if you wanted to know for each node, you wanted to know at what distance this is from node 1. For example, quickly you want to find out at what distance node 3 is from node 1 or node 7 is from node 1. Quickly, by quickly I mean in constant time. How you can do that? You can apply BFS. So this is our visited array. Okay, again we are going to use this visited array. Again, 1 2 3 4 5 6 7 8 9 and 10. 10. Okay, so now how the BFS works. So suppose you wanted to find out for each node at what distance they are from node 1. The distance will be measured using number of edges. For example, node 4 is at distance 2 because you have to go here and then here. And one more thing about trees is that there's always a unique path from one node to another node in a tree. Okay, so from node 1 to 4 there will be only a unique path because there are no cycles. So how BFS works? So BFS works in this manner. Since the problem statement is to find out distance of each node from certain node, which we'll be calling root, right? In this case, root is 1. So for each node, I want to find out the distance, the minimum distance from node 1. How you can do that? See, first of all, find out all of the node which are at distance 0 from node 1. So let's create another array which will store the distance of each node. Okay, so this I think I can make a little bigger. 2 3 4 5 6 7 8 9 10. So 1 2 3 4 5 6 7 8 9 and 10. Okay, so find out all of the node which are at distance 0. Which node is at distance 0 from node 1? Of course node 1 itself, right? So node 1 is at distance 0. Node 1 is the only node which is at distance 0 from our root node, right? We are evaluating distance of all other node from node 1, right? So node 1 is at distance 0. Now process all of the nodes which are at distance 2. How you can do that? See, sorry, no, at distance 1, because we have found out all of the node at distance 0. Now we need to find out all of the nodes at distance 1. How you can do that? See, all of the node which are at distance 1 are actually directly connected to node at distance 0, right? Node at distance 0 is this itself. So all of the nodes that are at distance 1 are actually these, this, this and this. Okay, these 4 nodes, we use different color for them, blue. So all of these nodes which are node 2 4 3 and 8 are at distance 1, right? And they will be directly connected to the nodes which are at distance 0, because from there to reach these nodes you have to take one edge, and that is why all of these are at distance 1. So node 2 4 3 and 8 are at distance 1. This is, so let me just do this. 2 3 4 and 8, 2 3 4 and 8 are at distance 1. Okay, now see here, we have found out these nodes which are at distance 1. How you will find out nodes which are at distance 2? Now see here, since this node is at distance 1 from the root, all of the nodes which are directly connected to this and are not visited, like these, must be at distance 2, right? Because this is at distance 1. To reach this, you have to go through one edge. That means this must be at distance 2, right? Making sense? And that's why all of the nodes which are directly connected to the nodes at level 1 and are not visited are actually at distance 2, because to reach those nodes you have to go through one edge, right? And that's why, again, different color, yellow, maybe yellow will not be visible, I guess red. So all of the node at distance 2 will be the node which are directly connected to one of these nodes. Okay, so node which is directly connected to node 2 and is not visited. So directly connected to node 2 and is not visited is clearly 5. So node 5 is at distance 2. Clearly you can see node 5 is at distance 2. See here, right? Sorry. So this. Okay, now for node 4, nothing is at distance 2 because from node 1 directly connected and is not visited. Nothing. Oh, I forget to mark them visited. When we found out node 1 is visited. When we found out node 2, 4, 3 and 8, 2, 4, 3 and 8, they are visited. And node 5 I just found out, so it is visited as well. So we have processed node 4 as well. Now let's go and process 3. Node 3, the node which are directly connected to node 3 and are not visited are these 6 and 4. So node 6 is visited and nodes. Why is this? There's no 4. I by mistake did this. Now, those nodes which are directly connected to node 3 and are not visited are 4 and 6. So 4 and 6 now we mark visited, and 4 and 6 will be at distance 2, right? Same goes for the other. Now we have process 3. Let's process 8. Nothing is there to add. That's gone. So we have processed all of the node at distance 1. After processing all of the node at distance 1, we are able to get all of the distance at all of the nodes at distance 2. Now to find the node at distance 3, what we have to do? We have to process all of the nodes at distance 2. So at distance 3. Process 5. What are the nodes connected to node 5 and are not visited? Of course 7. So 7 is at distance 3. 7, mark it 7. I'm not using different color this time, so forgive me about that. So 7 is now visited. Nothing to do with 4 because in 4 we have nothing which is unvisited. For node 6 there is nothing which is unvisited. So this is what you have found. For node 5 it is at distance 2. Node 4 is at distance 2. My bad. Node, what was, okay, this is actually 7. My bad. So basically you got the idea, right? First of all, you have to I messed up because of my 4 and 7 looks exactly the same. Actually, I'm not even sure. I think I wrote them 2 times because this is 7, I'm sure. I by mistake wrote 4 2 times, and I'm sorry for that. So 8, 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are only 9 nodes. So what is that is missing? 1, 2, 3, 4, 5, 6, 7, 8, and this is 9. Either this is 9 or that is 9. Sorry about that. So the basic idea is, first of all, find out node at distance 0. That will be your root itself. Okay, this will be at distance 0, and then using the node of distance 0, you can find out node of distance 1. Then using the node of distance 1, you can find out nodes at distance 2. Then using the nodes of distance 2, you can find out node as distance 3. What is happening? There is one important observation. You are processing nodes in the order of their distance. First you will process node at distance 0, then at 1, at 2, right? And this is also the order in which they are found. First of all, we found out node 0 nodes at 0 distance. Then we found out node at 1 distance, and then we found out nodes at 2 distance, and so on, right? So basically we are processing the nodes in the order they are found. And because of this, instead of creating a list and then processing them again and again, create a list of distance 0 element and then process this, create a list of distance 1 elements and then process them, and so on. Instead of doing that, what you can do, you can use queue. You can use queue, and using this, instead of creating this, you don't have to do that. Using this, you can actually process. You don't need to create extra list. So how you can do this using queue, let me show you, because if I don't show this with an example, this won't be clear. So again, I need Okay, 1 2 3 4 5 6 7. So what you do, you create a queue, and queue is, if you know, it follows FIFO procedure, right? First in, first out. The element which are inserted first will be processed first. That is exactly our need, right? So first what you do, you already know, since you have to find out the distance of every other node from node 1, right? So node 1 is your root. Distance of root is already 0, and in the queue you would insert node 1, and you would always process the node at the beginning of the queue. What you would do now, you would process node 1. How many nodes are at node 1 directly connected to node 1 and are not processed at this point? To show you, let me use this color. So this for now, because I don't want to go ahead and delete all of this, that will require extra time. So I'm going to use this to represent visited. Okay, this color to represent visited. Okay, so from node 1, the node which are not visited are, this is 9. Okay, this time I'm not going to fall for that. So 2 4 8 and 3. Okay, so you would insert 2 3 4 and 8, and distance of all of these will be 1 extra distance of this. Distance of node 1 is 1 0, so distance of all of these will be 1. So node 2 will have distance 1, 3 will have distance 1, this will have distance 1, node 8 will have distance 1. Pop out from the queue. Now this represents front of queue. Now what you'll do, you will process 2, and all of these nodes are of course visited. And now process 2, repeat the process again for node 2. And what you would do, you would see directly connected nodes that are directly connected to node 2 and are not visited. Directly connected to node 2 and are not visited is only one node, that is 5. So distance of 5 would be distance of this node plus 1. Distance of node 2 is 2. So sorry, distance of 2 is 1. 1 plus 1 2. So node 5 will have distance 2. And also whenever you find new node, insert it into the queue. So see here, we are using queue. We don't have to our requirement was to process the node as they are discovered, in the order they are discovered, and queue does exactly the same. As long in as early as you found certain node, simply insert it into queue. So if you found certain node at time 1, insert it into queue. Then you will find a node at time at least 2 or more, right? So basically they will be inserted into the queue in the order they are found, and they will be processed in the queue in the order they are found, because you always process from the front of the queue. That's why we use queue. Okay, if I show you the implementation without wasting much time. Okay, we need one more array, and let's remove this. BFS, what we do, right? We create a queue of int type. In the queue, I guess we use push function. Node 1, I don't even need to take this. Why I'm inserting 1? Because 1 is the root, and I need to find out the distance of every other node from node 1. Okay, so after that, what you will do, while there is at least one element, while the queue is not empty, okay, while the queue is not empty, process, what you would do, you would always take the element which is at the beginning. So in current node is equals to queue dot front, and after that what you will do, you will remove that element from the front. Okay, process this and remove it. So current represents the current node that we need to process, and what you will do to process current node, sorry, to process that, what you will do, in the adjacency list of current node, in the adjacency list of current node, you'll process each node one by one and check if this node is visited or not. If it is not visited, you need to insert this into the queue. So basically I was having 1, so current represents 1, and then in the adjacency list of node 1, what I'm doing, I'm taking nodes one by one and seeing whether they are visited or not. So in the adjacency list of 1, I checked, there was 4. When 4 is visited, the answer is no, so I'll insert 4 into the queue. Distance of node NODE is equals to distance of current node plus 1, right? And also mark node the node that we just inserted in the queue as true, that this is visited, and also push this into the queue. And also we have not defined the distance array in distance. So this is how your BFS works. So you create a queue, insert the root into it, and also distance of root should be 1, 0. After that, you process queue till it's empty. There is nothing to be left to be processed. Okay, each time bring out the first element to be processed, first element into the queue, and then remove that from the queue. After that, check in the adjacency list of that node whether there are some node which are not visited, and that is exactly what we are checking here. After that, distance of that node would be distance of current node plus 1. Now this is visited because we are inserting this into the queue, and this should work just fine. I don't know whether there will be some errors or not. After that, let's print distance of each node. Okay, let's see if we get any error. Okay, cool. Till now we are not getting any error, so let's run BFS on this same graph. Okay, so how many nodes we have? 1 2 3 3 6 9 9 nodes we have. One is connected to 4, one is connected to 2, one is connected to 8, one is connected to 3. Okay, 2 is connected to 5, 5 is connected to 7. Done. 3 is connected to, oh my god, 3 is connected to 9. Okay, 3 is connected to 9, and 3 is connected to 6. Distance of node 1 at least should have been, distance of node 1 should have been at least 0. Why it is not 0? Did we read n and then n minus 1 edges, a dot pushback b dot pushback a, then run BFS? There's a mistake in b. Oh, okay. Damn it. Sorry. You also need to mark the route unvisited, because if you don't mark it unvisited, see, I pushed this into the queue and did not mark it as visited. So when you reach this node and see if there is certain node which is directly connected to this and not visited, it will say, yeah, it is node 1, and it would insert node 1 again. And that is what was causing the problem. And that's why distance of node 1 was not coming 0. Let me just copy this test case so that I don't have to type it again. So again, important thing, when you are inserting the root, mark it as 0. Basically, mark it visited. Sorry, mark it visited, which is 1. 0 means unvisited, 1 means visited. Sorry, I'm taking too much stress. Okay, so here you see node 1 is at distance 0. Node 1 is at distance 0. Node 2, 3, and 4 are at distance 1, right? 2, 3, and 4 are at distance 1. And also, uh, node 8 is at distance 1, right? What node are at distance 2? 5, 6, and 9. So, 5, 6, and 9 are at a distance 2, and only node 7 is at distance 3. So, node 7 is at distance 3, right? So, this is how your BFS works. As far as the theory and implementation is concerned. And again, I have also covered this on my channel, so if you think that this is going too fast, again, someone has mentioned in the comment section, Striver also covered this, I have also covered this. So if you want to learn it slow pace, you can go to my channel, Striver's channels, or maybe Tushar Roy, or maybe other there, Gaurav Sen. There are many channels you can go to. Okay, so now I'll take questions after 5 6. Okay, this is 5 6, so we are ready for any questions. If you have any doubt, please go ahead and ask. Oh my god, my back hurts. Someone says you can work for us, please work for us, we are anonymous. What is this? How to find length of two nodes? how to find length between two nodes. Basically, you want to find the distance between two nodes, right? If you till I answer that, okay, it's all clear for Nipun at least. I'll wait for others' response as well. Thank you, Nipun. Prem Sagar asked how to find the length between two nodes. Good question. To find the length between two nodes, what you can do, you can run a BFS. That is a worst idea. What you can do, you can use LCA. You can use binary lifting. One of the techniques using LCA is binary lifting. In fact, to find the binary lifting is the technique using which you can find the LCA between two nodes. Once you have the LCA between two nodes, you can find out the distance between them in constant time. And using binary lifting, you can calculate the LCA of two nodes in log n time. So overall complexity between finding the distance between two nodes is log n. So to answer your question, where is Prem Sagar, to answer your question, you need to learn LCA, that is lowest common ancestor, and then you need to apply that. Using LCA, you can find out distance between two nodes in log n time. Okay. Okay, I'll try to come live on my channel as well. So I'm assuming we don't have, since I've asked 3 minutes ago, I don't think we have much questions in BFS section as well. So we have covered traversal techniques, graph tree representation. Now we are left with two important concepts. And Prem Saga, I told you to learn LCA, and we are going to cover LCA next. What is LCA and why to learn this? Both. Okay, so let's go ahead and learn LCA. Okay, remove all of these. Okay. One question. One question I'm going to ask you guys is this: if we keep this session interactive as much as possible, then this will be fun. Otherwise, this is going to be a dull session, and I'll be sorry if that happens. I'll be really sorry. So 5, note 6, notes 6, again. 1, 2, 3, 4, 5, note 7. So this is note 6. This is note 6, 8, 9, 10. Okay, so you guys, the next concept that we are going to learn next, I'll cover LCA after that. So question for you guys: if you are given a tree, this is that we are going to learn. You are given a tree, right? And you have to find the diameter of the tree. Okay, diameter, or you can print simply the length of the diameter. How you'll find that? So the diameter of a tree is the the maximum distance between any two nodes. So in this tree, I think this will be this 1, 2, 3, 4, 5, 6. So diameter of this tree is 6. So the question is, you are given a tree, how you'll find the length of the longest path, basically length of the diameter. Again, is there any question regarding diameter? Diameter is at least the definition of diameter is understandable, right? So the question is how you'll find the length of the diameter. Anyone knows? Because let's keep the session interactive. Otherwise, this is going to be a dull session. Anyone? Difference between ith q element. What is that? Difference between ith q element. See, to see Vinay, to find the difference, you need to have at least two elements, right? You are only telling difference between ith q element. Ith means only a single element. Uh, Please clear your question. The question is not clear. Please come again, Vinay. So Nishan says height of left plus right diameter. Okay, height on left plus height on right. Okay, comma, diameter on left, diameter on right. Okay, so what you are telling is actually dynamic programming approach. Yeah, this is one way to find. Nishant, the comment of Nishant says maximum of height of left plus height of right, comma, diameter on left, comma, diameter of right. This is actually recursive algorithm, which is uh, DP on tree. So there are two ways to find out diameter of a tree, longest length in a tree, and one of the ways is using DP. And Nishan's method that he has commented in the section is actually DP algorithm. Yeah, that is correct, Nishan. Root to child DFS, and after that, do DFS on childhood. Correct. This is the other way. I told you there are two ways, and one way is what Nishan told me, told to us, and other way is what Parth is telling. Okay, somewhat by DFS, not sure. Yes, you are absolutely right. In fact, both the method uses DFS. Rohan, you are absolutely right. There are two methods, one using DFS and one using DP, but even DP uses DFS. So yeah, in both the algorithms we are actually using DFS. So two times DFS, correct, Parthiv? Then निपुण ठीक है and calculate the longest distance from x naught. Yeah, correct, Nipun. And yeah, so most of the responses that I've got are absolutely correct. There are two methods you can find out uh, diameter of the tree, length of the diameter of the tree, and that is one using DP and another one only applying simple DFS. So one using DP on tree, of course, it will use DFS internally. Okay, clearly this will use DFS. And other method is without using DP, simply using DFS. So we are going to cover this on my channel. I have covered both of them, but DP one I won't be able to explain here in short time because I don't know whether most of you guys are very comfortable with recursion or not, because DP on tree specifically will use recursion no matter what. DP on tree 99% of time will use DFS, which is recursion. Okay, normal DP algorithm can be solved using using recursion or iteration. There are both of the approaches, but when you are working with tree, most likely 99% of the time you have to apply DP using DFS only. So without having the knowledge of recursion, you won't be able to apply DP on tree in most of the cases. I haven't seen any a single problem where I can apply iterative DP on tree. So I don't know about that. So basically we are going to apply DFS. How this works? Okay, the proof is interesting. I won't be providing the proof. That is more interesting. I have provided the proof on my channel, but that would again increase the length of this whole lecture. I cannot unfortunately do that. So if you can, please go ahead and learn the proof of this. Okay, that is interesting. So pick any node, doesn't matter. Pick any node, for example this, uh, use different color. Pick any node. Let's say we have picked node step 1. Let me write down the steps. 1, pick any node. I'm I mean I'm not able. First of all, my writing is very bad, and also when you're working with pen tab, it becomes worse. So pick a node, any arbitrary node, doesn't need to be anything. In this case, we have chose node 8. From node 8, find out the node which is at most distance from node 8, the farthest node from node 8. For example, this or this. Okay, one of these, right? So this is at distance 1 2 3 4. So this is at distance 4. 1 2 3 4. This and this both are at distance 4, right? So you can choose any node. Suppose you picked this. So choose a node, find out a node which is the farthest from this node, and we came to a conclusion and we chose this. It doesn't matter which node you choose if there are multiple, right? For example, in this case we have 3 nodes which are farthest from node 8. It doesn't matter, so pick anyone. We have picked node 5, and find farthest node. So we have picked node 5. From node 5, now when you find out the length, basically the longest length from node 5, and for your information, if you don't know, using DFS you can actually find the longest length starting from certain node. You can do this by DFS also or BFS also. Okay, so take step 2, take that node and find length of farthest node from this node. From this node. I know this is not readable, but okay. So step one is choose any node. In our case, we chose node 8. Find the farthest node. And the farthest node we picked was node 5. Now the second step is starting from node 5. Node 5. Find out the farthest node, the length of the farthest node. From node 5, the length of the farthest node is actually this, right? And I mean the farthest is this, and the length is 1, 2, 3, 4, 5, and 6. So length of the diameter is 6. This is how you find out diameter using two DFS. First DFS to find out the farthest node from any arbitrary node. Second DFS must be from that node. Okay, the node that you find out in the first step. From this node, run a DFS and find out the length of the farthest node from this node, which is this, the length of node 9 from 5, which is 1, 2, 3, 4, 5, 6. So this is your length of the diameter. So this is how you find out length of the diameter. Okay. I don't think we should have any what we say. We should not have any confusion in this algorithm, right? Do we have? If we have any problem, please post it down the comment section. I just want to say, I mean, I want to wait for like 2-3 minutes. If there is, please. If there is not, you can say okay, all is clear. Oh my god, my back. I'm waiting for 2 minutes. Okay. Are you guys there? Looks like I'm teaching to no one for now, but that's okay. I don't mind. Maybe you guys went for Code Forces contest that is today. I also want to participate in there. Okay, for next like 2 minutes, I'll also wait. If I don't get any response, that means we are all clear. Okay, we are clear. We are clear. We are clear. Thank you, Akriti, Vinay, and Nipun. Thank you for responding, Nipun and Vinay and Akriti. Akriti. So okay, so I'm since of course I've got response like we are clear, so we know how to find out the diameter. Okay, using DFS. There is one more approach like DFS. Sorry, using DP, and that is also interesting. So first of all I highly advise you guys to go ahead and learn the proof of this. Why this solution is actually correct. Why find the first node and then find the farthest node actually works. Okay, proof of correctness. Go ahead and learn that. You can prove this using proof by contradiction. So you will be able to understand that, because I always assume that proof by contradiction is the easiest way. Okay, so the last topic to cover today is the most important topic actually, LCA, that is lowest common ancestor. What is LCA? So we have a rooted tree, it have to be rooted, otherwise LCA won't be uniquely defined. 3, 4, 5, 6, 7, 8. Okay, so I'll wait for 2 minutes because Azan ho rahi hai. So clearly I'll wait for just 2 minutes and keep it on mute, and after that I'll continue. Okay, after Azan. Hello. Now let's go back to LCA. Thank you for waiting. So what is LCA? LCA stands for lowest common ancestor. For example, what are ancestor? For each node, first of all, the tree must be rooted. Rooted means there must be a root defined. Okay, so this is the root, and all of these are actually child of this node. Okay, this will be called the parent of the nodes of its subtree. So what is happening here? For example, this is parent of this node as well as all of the nodes inside it. Okay, so for this node, this and this, all of these nodes are actually ancestor. Node 2 and 1 are ancestor of node 3. Okay, for node 7, 3, 2 and 1, all of them are ancestors of node 7. So if you want to find, first of all, LCA is common ancestor, right? So you are given two nodes, for example 7 and 5, and you are required to find the lowest ancestor which is common to both. So if you see, for node 7, 3 is ancestor, 2 is ancestor, 1 is ancestor. Node 5, this and this is ancestor. What is the lowest of all common ancestor? If you see, 1, 2 and 3, all of them are common ancestor of node 7 and 5. Which one is the lowest out of all of these? Of course node 3. Okay, which is nearer to these nodes. So LCA of 7 and 5 will be node 3. What will be LCA of 4 and 7? Of course it would be node 2, because common is actually 2 and 1, right? And node 2 is the lowest one, so LCA of node 4 and 7 is actually 2, right? Using the LCA, you can actually find out the distance in constant time, right? This was the question asked. So see here, this is the root, so this is at distance 0, this is at distance 1, this is at 2, this is at 2, this is at 3, 3 and 1. If you want to find out the distance between node 4 and node 7, what is this? This is 3, right? So what you can do, you can take the distance of node A, which is 2, plus node B, which is 3, minus 2 times a distance of their LCA, 2 times 1, right? So it would be 5 minus 2, 3. So here you can see 1, 2 and 3. This way you are able to find out distance between two nodes in log n time, because to find the LCA it takes log n time. How? I'll tell you in a moment. So I'm just telling you, once you know the LCA, you can actually calculate the distance between A and B using this simple formula: distance of A plus distance of B minus 2 times distance of their LCA, and all of these distances from their root. Okay, all of these distances are defined from their root. So using this simple formula, using this simple formula, we are actually able to find out the distance between two nodes in constant time. But to find out this, it takes log n time. So the overall formula runs in log n time. Okay, so this is one of the major use cases of LCA. There are many. This is one of the. Okay, so the question is how I messed things up. So let's clear this up. So okay, so this is the tree. The question is how you will find the LCA. Okay, so the most efficient way is to find out using binary lifting. Okay, binary lifting. Okay, the spelling correct. I usually worry about the spelling because of course my vocabulary, my spellings usually are not correct. So using this technique, you can find out LCA between two nodes in log n time. How? See what you will do. You need to create a sparse array, and that is what I'm worrying about. So what you do, for each node you will keep track of its ancestor, okay, at power of 2 distances. Interesting, right? For node 7, it will be, for node 7 its ancestor at 2 raised let's just, for node 7, what we are going to do, again, for each node we need to store the ancestor of it at power of 2 distance. What does that mean? I'm explaining with an example. So 2 raised power 0 at 2 raised power 0 distance, at 2 raised power 1 distance, at 2 raised power 2 distance, and so on, right? For node 7, the node which is at distance 2 raised power 0, right, is this 3. Okay, so that is 3. For node 7, the node which is at distance, the ancestor which is at distance 2 raised power 1, which is at distance 2. At distance 2, we have this, right? So 2. Now at distance 2 raised power 2, that is at distance 4, that does not exist. So -1. Okay. So this is what we have to store for each single element. And for that, we need to create a sparse table. You can call that LCA table or whatever. And using this, you should be able to find out LCA between two nodes. How? I need to explain this with an example, and this is going to take time. Now, unfortunately, I cannot avoid this because, of course, this I have to explain. So suppose this is they are parting ways from here. 6, 7, 8. Okay. So I need to find out LCA of 7 and 8. This will come out here. So not here. Let's connect it here. Okay. 8 and 9. So you need to find LCA of node 7 and 9 first of all. How you'll find that? So see, we'll use binary lifting. For that, what we will do, we'll make them jump one by one. I mean upward at the point where they actually meet. If you see, you need to calculate the level of each node. For example, this is at 0 level, this is at 1, this is at 2, this is at 3, 4, 5, 6, and then this, sorry, this is not at distance 7, this is at distance 3. Okay, from the root, because root will be unique. So what you will do, first of all, what we will do, we'll bring both of them at the same level. Okay, and after that we'll move them together till the point where the node pointed by both of them, basically of the parent, is actually same. See what I'll do, I need to find LCA of 7 and 9, right? But 7 is at distance 6 while 9 is at distance 3, right? 9. Okay, so of course this is much deeper. First of all, what you have to do, you have to bring this at the same level as the other node, right? So make it jump. So what you can do, you can make it jump one by one. So this node becomes, let's say this is A, and this is A, and this is B. Okay, so now A becomes 6. Now make it jump again. A becomes 5. Now make it jump again. A becomes what? 4, right? A becomes 4, and now both of them are at same level. So first thing is, if they are already on the same level, do nothing. If they are not on the same level, pick the one which is deeper and make it jump upwards till they both are at the same level. But the question is, if you make it jump one by one, it would result in TLE, because suppose there are 1 million nodes, and the tree is something like bamboo tree. Okay, bamboo tree are like this. Okay, and there are a million nodes. I won't be able to, of course, represent all of them, and you have to find the LCA of node 1 and the node which is last in the 1 million node, right? So what you will do, you need to make it jump to reach it the same level as node 1, right? But to do that, what you had to do, you'll make it jump one by one, and that would require big O of n time, right? Because you have to go through all of those elements, and this will result in TLE. So what binary lifting does, it says, okay, instead of making a jump of length 1, okay, one by one, let's make jump in power of 2. And that is exactly the reason why we are storing their ancestor information in power of 2, right? So what it would do, see the difference between their uh, their level is actually 3, right? Because this is at distance 6, this is at distance 3, so 6 minus 3 is 3, so the difference is of length 3. So what you would do, 3 you can represent as 1 1. So first you would make a jump of length 0, 2 raised power 0 basically. So make a jump of length 2 raised power 0, who is 2 raised power 0th parent of node 7. We already have an array because we already have stored that, right? Just before that I explained, right? So what I'll do, I'll go to 2 raised power 0th parent. 2 raised power 0th parent is this. Now my A becomes this. From here, now this bit you have already covered. Now you need to take care of this bit. right? Because 3 you can represent 1 1, right? In binary representation, this is 2 raised power 0th bit, this is 2 raised power 1th bit, right? Now it says make a jump of length 2 raised power 1. From here 2 raised power 1, 1th parent, who is, it is this. So instead of making a jump of length 1, I'm directly making a jump of length 2. Now you see in 2 operation I am on the same level of node 9. To understand this better, suppose the difference between their nodes was like 12. Okay, one was at distance 15, one was at distance 3. So distance that one node need to cover was 12. How you'd cover that? See, binary representation of this should be 8. This, my bad. Okay, okay, this is 12, right? In binary representation, this is 2 raised power 0, 2 raised power 1, 2 raised power 2, 2 raised power 3. Okay, so this is how 12 will be representation. To make a jump of 12, instead of going one by one, what it will do, it will check the 0th bit. 0th bit is not set, so you won't make a jump of length 2 raised power 0. Okay, so you won't go and see who is my 2 raised power 0th parent, that is direct parent. Okay, so 1th bit is also not set, so no jump of length 2 raised power 0. Second bit is actually set for this node, who is the node at distance 2 raised power 2, which is 4, right? So you directly make a jump of length 4. So now you have already covered length 4 in a single jump. So see what is happening here. And after that, the next bit is 3. So from that node, you need to make a jump of length 2 raised power 3, which is 8. That node already stores the information of 2 raised power third parent, right? So you directly make a jump on that node. So using binary lifting, this is called binary lifting because you are making jump in binary steps. 2 as per 0 step, 2 as per 1 step, 2 as per 3 step, right? And that is how you'll be covering this. So at max, how many jumps you can take? Log n jump, right? Because each number can be each number, if you want to represent it in binary bits, takes log n space. All you have to do is log n jumps, and that's why in log n jump these two will be on the same level. Once a is here, b is here, basically both of them are on the same level. You need to check whether both are same or not. For example, if this was the tree and I wanted to find the LCA of 1 and 3, what I'll do, I'll make 3 jump, right? So 3 would go from here to here and then from here to here. Now after reaching, b is here, a is also here. Now since a and b are same, this itself is the LCA. So if after making all of the jump, basically if after they both come to the same level, if a and b are same, that means a basically those two itself are the LCA. So you can directly return either a or b, that itself is the LCA. Otherwise, what you can do, now you have to, for example, this was the case when you have to stop directly, because after making the jumps to make them on the same level, both of them are pointing to the same node. That means this itself is the LCA. If that not happens, that is this case, if they both are still pointing to the different node, again we'll start making jumps of maximum length, right? So what I'll do, I'll try to make a length if when you are processing, you define maximum power to which you can make jump. See, I told you you don't have to make what is the maximum length of a tree. If there are n nodes, tree can be of n minus 1 length, right? The distance, maximum distance can be 2 n minus 1, right? So I'm assuming n. So if the maximum length can be n, then you can have at max log n number of jumps. Why? Because at max the first jump is of length 2 raised power 0, right? The next is 2 raised power 1. If you take like a 10th jump, it would be 2 raised power 10, right? So this x, 2 raised power x, must be less than equals to n. So x must be less than equals to log base 2 n, right? And that is why number of information, the number of parents that we'll be storing are not more than log n for each node. So what I'll do, I'll define first of all log n, which will be roughly 20 if n is 1 million. If there are 1 million nodes, at max you have to store the parent at 2 raised power 20th distance. Okay, not more than that. So I'll start with 2 raised power 20. Does 2 raised power 20 parent exist for 4 and 3? The answer is no. 2 raised power 20 is roughly 1 million. 1 million parent does not exist. Go for 2 raised power 20, 2 raised power 19 doesn't exist, 2 raised power 18 doesn't exist, dash 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 till 2 raised power 2. 2 raised power 2 parent exists, 1 2 3 no, uh, because this is at distance 0, this is at distance 1, this is at distance 2. So at max 2 raised power 1th parent exists, right? So 2 raised power 0th parent exists for this node and for this node, and 2 raised power 1th parent exists. This is 2 raised power 0 and this is 2 raised power 1th parent. Even 2 raised power second parent does not exist, which will be parent at distance 4, right? So 2 raised power 1th parent exists, so I'll try to make a jump of length 2 raised power 1, right? Node at 2 raised power 1 is this. Should I make or not? So we need to make them jump till the point where their parent are actually same, right? So if till the point where they should not point to the same element. If I make a jump of 2 s power 1, this node will point to this and this node will point to this. I know this is getting messy, but unfortunately I had to finish by 7:30, but it is already 7:40, so I cannot take a lot of time, because I know you might be thinking that this is a lot to take in, and that is absolutely true. On my channel I took like 2 hours, one and a half hour only to explain this technique, two or three different lectures. Okay, so of course in short time I won't be able to explain, and you won't be able to understand it fully, but try to understand as much as possible. So after reaching the same level, I want to make a length of 2 s power, make a jump of length 2 s power 1. 2 s power 1, you this and this both will reach here, but now we should avoid a jump where both of them will point to the same node. If I make a length 2 s power 1 length jump, both of them will point to the same node, so I should not make a jump of this. Okay, so I should not make. So now make a jump of 2 s power 0. So from here I would reach here. After you are done with this, after you have made a length 2 s power 0 jump, you are done. Okay, so now both of them are pointing to this. After that, what will happen? Their immediate parent will actually be the LCA. So if I explain with a better example with less violence on the screen. Here, a better example for you. 3, 4, 5, 6, 7, 8. So both of them, this is A, this is B. Both of them are on same level, right? So what you would do, you would say, okay, start from the maximum one. 2 s power 20 doesn't exist. 2 s power 19, 2 s power dash 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 dash, 2 s power 3. 2 s power 3 means parent at distance 8. Parent at distance 8 doesn't exist. Go for 2 s power 2. Parent at distance 4. So at distance 1, 2, 3, 4. Yeah, parent at distance 4 exists. So should I make a jump of 2 s power 2? The answer is no. Because if you make a jump of 2 s power 2, both of them will be pointing to the same node, and this we should avoid. Because of course their LCA is this, and if we make a jump of length 2 s power 2, or if there exists another node above them, they will actually miss out the original LCA. That's why we never make a jump after which both of them point to the same elements. So since there are 2 s power second parent is actually same, we won't make this jump as well. So we will go for 2 s power 1. 2 s power 1th parent exists. Yes, 2 s power 1th parent exists for both. So make a jump of that. And after the jump, will they be pointing to the same node? The answer is no. So of course, make a jump of length 2 s power 1, and now they are pointing to this node and this node, right? After that, we have taken care of 2 s power 1. We'll go for 2 s power 0. Should we make a jump of 2 s power 0? If I make a jump of 2 s power 0, they both will be pointing to node 2, which is same. So of course, we would not make a jump of 2 s power 0. As soon as you reach 0, your for loop stops. So start your loop from 20, because there can be a million node depending upon that. Because if there are a million nodes, roughly 2 s power 20 is a million. That's why I take 20. Okay. So now starting from 20, we go till 0. And as soon as you complete 2 s power 0, their immediate parent will actually be LCA. So this is how you apply binary lifting. Again, I'm sure this will have a lot of doubts. I'll take questions, but I'll answer only those which I can answer in the given time constraint. Otherwise, you can go to my channel. I've already covered that. Uh, that was, I took like 2-3 lectures of like 35, 40 or 40 minutes to cover this 2-3 lectures. So I think implementation was in a separate lecture. So yeah, this is a lot to take in, and understanding this is very, very important because you will be using this. Let me tell you where this will be used. So that will be an important information for you guys. Well, this LCA will be used. So see how where this LCA is used. First of all, find distance between two nodes. Okay, this is between two nodes. It is actually an easy algorithm. Okay, this will come under easy. Second, how you can utilize LCA. Well, there are worst algorithms. You can apply in, I guess, in most of the centroid algorithm, centroid decomposition. In most of the centroid decomposition uh, algorithms, you will be actually using LCA. That is medium hard. Three, with centroid decomposition, there is also heavy light decomposition, HLD. This is actually hard algorithm. Okay, there also you will be applying binary lifting. So binary lifting is not something that only is used to find out the distance between two nodes. I think there are more use cases of HLD, what I'm saying, binary lifting, but these two are very important. Heavy light decomposition, it is actually a hard algorithm or data structure, whatever you want to call, and it uses internally segment tree and this and that and a lot of things. And the same goes for centroid decomposition, and both of them actually use binary lifting to answer queries. And also, yeah, I forget to mention that there are queries on tree. When you are working with queries on tree, like square root decomposition, Mohs algorithm, you most likely be working with LCA. So it is very, very important and highly recommended that you learn LCA. Learning LCA is not that difficult, but their implementation, their use case in some of the algorithms like central decomposition, Mohs algorithm, query on tree, it is just very beautiful. I mean, its implementation and use cases are so diverse. So I'll highly recommend you to go through this. Okay, and of course this should have for most of you guys, you would have not be able to understand it completely, and that is absolutely correct. I mean, that is absolutely fine, because in short time you won't be able to understand this completely. So uh, I already have lecture on this, covered this, and also I have practice problems as well which cover this, so you can go through all of them so to understand this better. I have this lecture to implement how this work, how the implementation work. After that, I've covered the uh, problems as well, practice problems, so you can go through that practice problem, implement it yourself, so you understand, okay, you are able to understand it correctly. So yeah, this was all for this session. Uh, if I don't know, should I even ask if is there any suggestion for if, yeah, I also have a session next time. So is there any suggestion for next session or anything you would like to pass comment on? Nipun, you are absolutely right. That's what I just said. Understanding this in short time is very, very difficult. So that's completely fine. If even if I had this much knowledge that I currently have and I had to learn certain new things, uh, I will have the same response as you had. So you guys, any suggestion for the next session? Because this is where we stop. We have covered all of the topics that we had to cover in today's session. And if you feel that, yeah, there might have been some algorithm that should have taken extra time, so you can go through, of course, you can go to any channel like uh, I guess the channel name was Take You Forward, or my channel. There are many. You can go through them and learn in detail. Okay. So no suggestion for the next session, guys? I'll wait for 2 minutes. 7:49. Okay. So if you have suggestion, okay. Thank you, Nipun. So okay, if there are no suggestion, of course, I'll see you guys in the next session when I think I have the next session on 17. So see you guys there. Thank you, Nipun, and thank you all of you guys. Thank you, Shah. I appreciate that. Anurag, we can finish that. I mean, we can finish this session now. And thank you guys for having me. It was really a great session, and thank you all of you guys for joining in and being as much interactive as possible. So yeah, thanks to all of the audience as well, and thank you Anurag and the DSA Carnival organizers to have me. Thank you guys.
Okay, so thank you so much, Waqar sir, for this knowledgeable and interactive session. And I hope all the students were enjoying a lot. And uh, yeah, and took a deep dive into the trees topic. Also, thanks a lot everyone for joining the session and making it interactive and successful. Okay, so yeah, our quiz winner for yesterday is Ujjwal Singh from Delhi Technical University. Okay, and he'll be provided a T-shirt from Prep Bytes. So you can also get a T-shirt. So don't forget to attend today's quiz. The quiz link is given in the description box, also in the chat box also. Okay, so thank you all for joining the session. See you tomorrow with another topic and another expert. Till then, stay safe and keep learning.
Yes.
Once again, thank you, Waqar sir.
Bye, guys. Thank you, Anurag. Bye, guys.
Okay. Bye, everyone.